So, what happens to geometry when you take away its most fundamental reference point, the origin? Today, we're diving into affine space. It's this really powerful mathematical structure that kind of forces us to rethink the difference between a location and a direction. And it elegantly separates the idea of a point from the idea of a vector.
Here's the plan. We'll kick things off with a simple question that really messes with our usual geometric intuition. Then we'll build up the formal definition, see where this idea pops up in the real world, and figure out why forgetting the origin is such a powerful move. Finally, we'll look at the special operations this new perspective opens up for us.
Okay, let's start with a question that seems almost ridiculously simple, but it's actually got a lot of depth. We're all used to adding vectors, head to tail. But what would it even mean to add two locations, two distinct points in space?
To really see why this is a problem, let's imagine we've got two people, Alice and Bob. They're both looking at the exact same 2 points, A and B. The catch is, Alice has her own coordinate system with her own origin, and Bob has his somewhere else. Now, if we ask them both to do the same thing, add point A to point B, are they going to agree on the answer?
Let's actually walk through their calculations. For Alice, it's easy. Her origin is the standard 0. So adding points A and B is just simple vector addition from her perspective. But for Bob, who's starting from his own origin P, things are way different. First, he has to figure out the vectors that point from his origin to A and B. Those vectors are A minus P and B minus P. Then he adds those vectors together and applies that combined shift to his starting point P. And as you can see, they get completely different results. This proves it. Adding points isn't a well-defined operation. The answer you get depends entirely on where you decide your origin is. So the real issue here isn't the points themselves. It's our reliance on this one special, privileged point we call the origin. And this leads us to the huge question behind affine space. What kind of geometry do we have left when we build a system that has no origin at all? All right, so how do we make this idea rigorous? Let's get into the mathematical structure of this origin-free geometry. An affine space basically has two key ingredients. First, you've got a set of points, which we'll call A. These are just pure locations, nothing more. Second, you have an associated vector space, V. Now, the crucial thing here is that the vectors in V are not points. They are pure displacements, or translations. The main rule is that vectors from V can act on the points in A, essentially sliding them from one spot to another. This structure gives us a very specific and very clear set of rules. You can add a vector to a point to get a new point. That's just a translation. You can subtract one point from another, say B minus A, and the result isn't another point. No, it's the unique displacement vector V that takes you from A to B. And of course, you can do all your normal vector stuff, like adding two vectors. But notice what's missing. You absolutely cannot add 2 points together. That operation is out. This whole relationship is formalized by what are called Weyl axioms. The first one is pretty straightforward. It says for any starting point A and any displacement vector V, there is exactly one unique point B that you can land on. The second axiom, well, it's just the classic triangle rule for vectors, but in disguise. All it's saying is that the trip from A to B, followed by the trip from B to C, is the same as taking the direct path straight from A to C. This just makes sure our whole system of displacements is consistent and makes sense. Now, I know this might seem a little abstract, but trust me, affine spaces are hiding in plain sight all over the place in math and physics. Let's look at some real examples. The most familiar example is just good old Euclidean space. You can think of r squared or r3 as a set of points, and the vectors we all know and love are the displacements. Now, think about a vector subspace, like a flat plane that cuts right through the origin. But what if you just nudge it? You translate it so it no longer contains the origin. What you have now is a perfect example of an affine subspace. It's still a flat surface, it just doesn't have a special 0 point on it anymore. And the concept is incredibly broad. For example, if you look at the set of solutions to a linear system like Tx equals b, the kind that often describes a line or plane that doesn't pass through the origin, that solution set forms an affine space. Physical space itself, before we go and draw any axes on it, is fundamentally affine. You can even think about time this way. Specific dates, like July 4th, 1776, are points. And durations, like 3 days, are the vectors that move you from one date to another. Okay, so why? Why go to all this trouble to just forget the origin?
What's the payoff? What do we gain from thinking this way?
This is really the key question. If you can't measure distance from some central point anymore, what geometric concepts are still valid? What properties are actually inherent to the space itself, instead of just being artifacts of the coordinate system we decided to slap on top of it?
Well, the answer is that the properties that are independent of an origin, what we call affine properties, are the ones that stick around. Think about it. Whether two lines are parallel doesn't change just because you shift your point of view. The same goes for the midpoint of a line segment. Affine geometry is all about preserving these kinds of relationships. It doesn't really care about concepts like absolute distance or angle measurements, because those things really depend on having a fixed point to measure from.
So this origin-free way of thinking leads to some pretty special kinds of operations and transformations that are perfectly designed for this environment.
Remember how we said adding 2 points was a total no-go? Well, there's a loophole, a special type of combination that is well-defined, the affine combination. The best way to think about it is as a weighted average of points, with one big rule. The weights all have to add up to 1. The result you get is a new point called the barycenter, which is basically the center of mass, and its location is exactly the same no matter where you place your origin. This is actually the foundation of barycentric coordinates, which is a really cool way to describe a point's location relative to other points, not to some arbitrary origin.
This also changes how we think about transformations, A linear map in a standard vector space has to keep the origin fixed. L of 0 has to equal 0. But an affine map is more general, more free. It's basically a linear map, like a rotation or scaling or a shear, that's followed by a translation. It preserves the essential structure of the affine space, like keeping parallel lines parallel, but it's not tied down to a fixed origin.
All right, let's zoom out and put all these pieces together. What's the big picture here? The mathematician Marcel Berger just nailed it with this quote. An affine space really is just a vector space where we've deliberately forgotten about the origin. And by doing that, we gain this incredible freedom to translate our entire frame of reference anywhere we want.
And that's really the heart of it. Affine space isn't just some abstract curiosity. It's the essential bridge that lets us apply the powerful, structured tools of linear algebra to the fluid, intuitive world of geometry. It gives us a language to talk about space before we impose an arbitrary coordinate system onto it. So I'll leave you with this question to chew on. This idea of an origin-free geometry isn't just elegant, it's incredibly practical. How does thinking this way unlock new possibilities in computer graphics, where we're constantly moving and transforming objects? Or in algebraic geometry, where we study these complex shapes defined by polynomials? That freedom from the origin, that's where the real power is.